Okay, hello. This is section 5.1, the natural logarithmic function and differentiation. So, the natural logarithmic function for integration. So, general power rule that was how to integrate with the power rules. Okay, so when we have a power rule, we need to integrate this way and plus c because there's always a constant, such as we call the general power rule has an important disclaimer. It does not apply when n equal to -1. So consequently, and you have not yet found the antiderivative for the function f of x equal to 1 over x. So in this section, we will use the second fundamental theorem for the calculus to define such functions. So it is neither algebraic nor trigonometry, but falls into the new class of functions called the logarithmic functions. This particular function is the natural logarithmic function. So definition of the natural logarithmic function. So when you have a ln, which is ln is a natural log because base is e, and the integration between limit 1 to x 1 over t dt and x is greater than 0, the domain of the natural logarithmic function is a set of all positive real numbers. So from this definition, you can see that the ln x is a positive for x is greater than 1. Otherwise, you get the undefined case. And the negative will get the x must be 0 to 1. So never equal to 0 or negative. As shown as a figure 5.1 in here. So moreover, ln 1 is a 0 because the upper and lower limit of the integration are equal to when x equal to 1. So this is a case of x is greater than 1. Then the ln x is always going to be positive. Between the x is 0 to 1 is x is always a negative. Alright, so the ln x is negative. To sketch the graph of y equal to ln x, you can think of the natural logarithmic functions as antiderivative given by the differential equation. So dy dx equal to 1 over x, and then the y equal to ln x is going to be of the form of this, okay? So figure 5.2 is a computer-generated graph called the slope field or direction field. So as you notice, there's directions of the small line in here. And then showing the small line segments of the slope of 1 over x. And then graph of y equal to ln x is a solution that passes through the point of 1, 0 right here. So each small line segment has a slope of 1 over x. So next, the theorem is some basic property of the natural logarithmic function. So property of the natural logarithmic function. The natural logarithmic function has the following properties. So domains are always the not equal to 0, but always positive numbers, and the range is going to be all real numbers. And function is always continuous, such as there's no break or jump, increasing, and then always 1 to 1. And the graph is concave, always downward. Alright, using the definition of the natural logarithm function, you can prove the several important properties involving operation with the natural logarithm. So if you are already familiar with the logarithm, you will recognize this property listed below the characteristic of all logarithm here. So logarithmic property, which is a and b are always positive number, which is that's actually the number next to the log, and the n is a rational, and then the following properties are always true. So ln 1 is always equal to 0. Ln ab you can split as ln a plus ln b, which is the product always becomes sum of the log. And then there's a power rule. We can always put the n as a power next to the power exponent next to the ln a. ln is already exponent too. And then when you have a quotient, it always makes a difference of 2 log. Expanding the logarithmic expression, so when you have ln 10 over 9, which is the same as ln 10 minus ln 9, and the ln square root of 3x plus 2, which is we can change the square root as a half power, and then the half power you can put it in the front as a factor times ln 3x plus 2. And then you can also split it as a ln 6x minus ln 5, also 6 as a product, so you can also have the sum of the two ln 2. And then ln of this form, so you can split it as a quotient as a difference, okay? And then there's a power 2, we can pull it in the front, and the ln x squared plus 3, but there's nothing you can do about this one. And then minus of, and the x is already product of the x and this, so x is a sum of another ln, and then this the whole thing you can put it out, but change to the cube root as 1/3 power. And then that one you can distribute the negative, and then it's going to be negative, and then you can also pull out the 1/3 as the factor of the next to the ln. Alright, natural logarithmic function. So when you're using the property of the logarithm to rewrite the logarithmic function, so you must check to see whether the domain rewritten function is the same as the domain of the original. So for instance, the domain of the f of x in equal to ln x squared is all real numbers except x equal to 0, because the ln 0 cannot be possible. And of the domain of the g of x equal to 2 ln squared is all positive real numbers. So when you have this, and this is a graph that we get, but this is a 2 ln x cases, okay, because we need to only choose the x is a positive. So the number e that we can think about it, so it's likely you have studied the logarithm in an algebra course. There, without the benefit of the calculus, a logarithm would be being defined in terms of the base number. For example, the common logarithm has a base of 10, and therefore the log base 10 of 10 equal to 1. The base of the natural logarithm is defined using the fact that the natural logarithmic function is continuous and is also one-to-one, and the range of the negative to infinity. So that there must be the unique number x such that ln x is always equal to 1, as shown as a figure over here, always crossing that one. And then this number is denoted by the letter e, which is an irrational number that is has the following decimal approximation as this one. Alright, so the next graph showing that the e is a base of for the natural logarithm because of the ln e is a 1, so this is y equal to 1 over x graphs. And then definition of the e is ln e is the same as integration from the 1 to e 1 over t dt equal to 1. So once you know that ln e equal to 1, you can see the logarithmic property to evaluate the natural logarithm of the several other numbers. So for example, by using the property ln e to the n same as n times ln e is the same as 1, so it becomes n. So you can evaluate the ln e to the n for the various value of the n as shown as a table in here, and then the figure 5.6 has the pictures. So x and the ln x, which is you plug it in the ln, come out as these numbers. So it's going to be same as exponents from the expression. And then evaluate the natural logarithmic expressions. ln2 is about 0.693. ln 32 is about 3.466. ln 0.1 is about negative 2.303. So derivative of the natural logarithmic function, derivative of the natural logarithmic function is given theorem 5.3. So first step of the theorem follows from the definition of the natural logarithmic function as the antiderivative. The second part of the theorem is simply the chain rules. Okay, because you have instead of the one, you got something else, so we have to use a chain rule to version of the first part. So theorem derivative of the natural logarithmic functions, let u be the differentiable function of x, and then d dx ln x same as 1 over x, and then the d dx ln u is 1 over u, du dx, that which is a u prime over u. So u must be always positive to x must be positive too. So differentiation of the logarithmic functions, d dx ln 2x is you need to differentiate the u, which is a 2 over same as a u 2x, and then just simplify, that'll be the 1 over x. So you can just u as a 2x here. And then d dx ln x squared plus 1, so u is x squared plus 1, so u prime is 2x, and the u is x squared plus 1. This is how you differentiate. dd over x, x ln x, and then you can use as a separate as so x times d dx ln x, and then use the product rule, right? And then the ln x and d dx as x, and then you can simplify from here. And then you can use a power rule, so pull out the 3, and then ln x and square, and also you need to use a chain rule to differentiate the ln x too, so which is what we got here. Alright, so now let's look at the example. Okay, so find the derivative of the function. So the h of x is ln of 2x squared plus 1, so h prime of x is, okay, so we have to say u is going to be the 2x squared plus 1, which is u prime is 4x, okay, so this becomes u prime over u, so 4x over 2x plus 1. Same as here too. In order to find the y prime, ln of, right, so let's say u is x squared minus 4, And then u prime is 2x. Okay. So what I can do is in here, which is before I do this, actually I want to put it this way. So y equal to, I'm going to rewrite it. So it's ln of x squared minus 4 half power, which is a y equal to same as half of ln of x squared minus 4. And then y prime will be half of, and then u prime, which is a 2x, over u, which is x squared minus 4. And then when you simplify it, 2 cancels out. You got x over x squared minus 4. Alright, now h of t, right? So this is we have to use quotient rules. So h prime of t is, okay, so for those here, so you need to put the t square and then keep t, and then you got a dt of ln t, which is 1 over t, subtract, and then keep the ln t, and then t becomes 1, and then you just need to simplify. So this is going to be 1 minus ln t over t squared. For the fourth one, f of x equal to ln of x plus square root of 4 plus x squared. So this one, I can put that as, I want to put that as ln of x plus 4 plus 4 plus x squared to the half power. And then a prime of x is, and then I need to use as so u is x plus 4 plus x squared to the half power. So u prime is 1 plus half of 4 plus 4 plus and x squared, and then use a chain rule. 1 half is a negative, the 1 half minus 1, and then times by chain rule 2x. Okay, so now f prime of x is u prime, which is a 1 plus 1 half of 4 plus x squared to the negative half power of the 2x over u, which is x plus square root of 4 plus x squared. And then you will see that is 2 cancels out, right? So you got 1 plus x, I want to pull the x out, and then 4 plus x squared to the negative 1 half power over the x plus square root of 4 plus x squared, okay? And then I want to multiply by x minus, because I want to rationalize it, 4 plus x squared both sides. And then I get that as, by multiplying, I get that as x minus square root of 4 plus x squared and plus x squared of 4 plus x squared with a negative half power and minus x. And then x squared minus 4 plus x squared. And then if I simplify this, because this x cancels out, I got negative square root of 4 plus x squared plus x squared of 4 plus x squared negative half power over negative 4. And then if I factor out the 4 plus x squared to the negative half power, and then I get as negative 4 plus x squared over negative 4. And then I simplify as 4 plus x squared to the negative half. And then it becomes a negative 4 over negative 4. And negative 4 cancel. And then I can put that as 1 over square root of 4 plus x squared. Okay, that's all. Yeah, it takes a while to get the answers for this one. Okay. For the E, I want to change to the half power instead of the square root. So 2 plus cosine square x to the half power. And then y prime is u prime, which is 2 plus cosine square. Oh, and then I can put that as half of, right? And then ln of 2 plus cosine square x. And then I got the half in here, and the u prime is 2 is going to be 0. And then power rule, negative 2 cosine x. And then the cosine x is chain rule as a sine x. And then it becomes a u plus 2 plus cosine square x. And then in here, the 2 cancels out. And then you get the negative cosine x sine x over 2 plus cosine square x. Alright, next page, please. So find the derivative of y equal to x minus 2 square over square root of x squared plus 1, which is x is not equal to 2 in this case. So this time I want to do it a little different way. Okay, so for that, I want to put down as I want to put the ln both sides. You can do this. So ln of you got x minus 2 square over square root of x squared plus 1, which is ln. Now you have an ln. We can use the quotient rule. So we got ln of x minus 2 square subtract ln of square root of x squared plus 1. Now ln wise, now you can apply the power rule. So 2 ln of x minus 2 minus, and I can pull out the half of ln of x squared plus 1. Now I want to derivative both sides. So sorry about that. So it's going to be y prime over y, which is 2 times of if the u is x minus 2, so u prime is 1 over x minus 2 minus half times u prime is 2x over x squared plus 1. And then y prime of y. Now simplify this. So I got 2. You need to actually find the LCD to multiply together. You get the x squared plus 2x plus 2 over x minus 2 times x squared plus 1. And then solve for y prime, which is y is as x squared plus 2x plus 2. I don't need the parentheses, right? Plus 2 over x minus 2 times x squared plus 1. And then y prime is, now the y is originally the x minus 2 square, which is, I'm talking about this, okay? And so I want to plug it in as, I got as x minus 2 square over x squared plus 1 in square root, and then times by the x squared plus 2x plus 2 over square root of, not the square root of, sorry, as x minus 2 times x squared plus 1. And then there is a cancellations in here, so I can cancel that out. So I cancel as one of this to this one, and I can put this thing together, right? So if I simplify that, y prime is now the 1x minus 2 times of x squared plus 2x plus 2. And denominator, I can say x squared plus 1, and the half plus 1 is 3 over 2. So this is actually the y prime. It takes a kind of while to find the answer though. That's okay. Because the natural logarithm is undefined for the negative numbers, you will often encounter expressions for the form of the ln absolute value of the u that always makes a positive number. The next theorem states that you can differentiate function of the form y equal to ln absolute value of the u, although the absolute value notation was not present. So the theorem derivative involving the absolute value is we got this way. So find the derivative of y equal to secant x plus tangent x. So dy dx is u prime. So the derivative of the secant x is a secant x and tangent x. And then derivative of the tangent x is a secant square x. And then u secant x plus tangent x. And then I need to simplify, which is pull out the secant x. I got tangent x plus secant x over secant x plus tangent x, which is cancels out, equal to secant x. Alright, next page. Use implicit differentiation to find the dy dx. Okay. So differentiate each of the terms. So ln x and y. So I need to use the chain rules. So ln the logarithmic property, right? So ln x plus ln y plus 5x equal to 30. And then the differential to ln x remains 1 over x plus 1 over y. We are different in terms of x, so it's going to be dy dx. And plus 5 equal to 0. And then we are solving for dy dx, so we need to subtract the 1 over x both sides, subtract the 5 both sides. I got 1 over y, dy dx becomes negative 1 over x minus 5. And then multiply by y both sides. And then I got dy dx is negative y over x minus 5y. And then I think that'll be all, but if you go further, you can just put the x as LCD and negative y minus 5x xy. And then if you pull out the negative, you can say y plus 5xy over x. So either one is a possible answer, okay? Use differentiation to find the equation of the tangent line to the graph at the given point. So we're going to differentiate in terms of x. So y squared means 2y and chain rule dy prime. And then you can use split it out, or you can use a quadrant. Okay, so product rule this time. So ln, which is xy derivative, is going to be xy prime plus y over xy, which equal to 0. And then we are isolate the y prime. So we're going to actually multiply by xy both sides. And then you get 2x y squared y prime plus xy prime plus y equal to 0. And then I want to actually solve for y prime, okay? So subtract y both sides, which is I got 2xy squared y prime plus xy prime equal to negative y. And factor the y prime, I got 2xy squared plus x equal to negative y. And the y prime is negative y over 2xy squared plus x. And then plug it into the order pair of the en1. And then you get the negative 1 over 2 times of e to the negative 1 squared plus e, which is a negative 1 over 2e plus e, which is a negative 1 over 3e, which is that's a slope, right? So now in order to find the tangent line, which is y minus y1 equal to m times x minus x1. So y1 is 1, m is negative 1 over 3e of x minus e. And then when you solve for y, it becomes negative 1 over 3ex and plus 1/3 and adding it 1. And then y equal to negative 1 over 3ex and plus 4/3. Okay, so that's all. Alright, next page. Locate any relative extrema and inflection point, okay? So, in order to find the extrema, we need to find the first derivative, right? So, y prime is 1 minus 1 over x. Now, we set the y prime equal to 0. And then 1 over x equal to 1, which is x equal to 1. And then if I get the y double prime, which is going to be the 1 becomes 0, negative 1 over x becomes 1 over x squared. But this is always a positive, which means this is give us a minimum. So when x equal to 1, which is plugged in. So y equal to 1 minus ln 1. So y equal to 1 because ln 1 is a 0. So it's a 1, 1. Okay, so this is actually the relative minimum. And then this state is always passed. So when you set the y double prime, which is 1 over x squared equal to 0, which is 1 over x equal to 0, so x squared equal to 0, which is x is a 0. But as a domain, I cannot use x equal to 0. So in this case, there's no inflection point. Alright, then the last one. Okay, y equal to ln x over x. So y prime is use a quotient rule. So you got x squared. So x and 1 over x. Subtract the ln x. And then set equal to 0, which is 1 minus ln x over x. So x must be the e. So in order to find the minimum or maximum, we need to find the second derivative from here, which is I'm going to find from here. Okay, so I get the x to 4 of x squared of negative 1 over x and minus 1 minus ln x of 2x. And then I get the 2 ln x minus 3 over x cubed, which is always stays a negative. So this gives us the maximum. Okay, so plug it in. So if you get the y equal to ln e over e, which is a 1 over e. So e and 1 over e is a relative maximum. And also, if you set the y double prime equal to 0, which is 2 ln x minus 3x cubed, and 2 ln x equal to 3, ln x equal to 3 over 2, x equal to e to the 3 over 2, which means e to the 3 over 2, and plug it into the y equal to ln x over x, you got 3 over 2 e to the negative 3 over 2. That becomes an inflection point. Alright, so that's for the 5.1. Thank you for listening.